Good evening, everyone. So today will be the next second lecture of the kinetic theory of gases. We'll be starting with the Gay-Lussac's law, right, for the ideal gases, and then we'll be also discussing about Maxwell Boltzman distribution of speeds at different condition for a given gas, right? So we'll be starting with Gay-Lussac's law, and according to this law, for a given mass of an ideal gas, right? If the volume of a given mass of ideal gas is constant, pressure of gas is directly proportional to the temperature, right? It means that if the volume is kept constant for a gas which is placed or which is kept in a container, right? Let's suppose it's the container, and in this container we have some moles of the gas, right? Let's suppose n moles of gas are there, right? N moles of gas are there, and the volume of this the volume of this container, right? The volume of this container is a constant, right? Is constant, right? The volume of this container is constant, right? The volume of this container will remain constant only if we just close this container, right, from both sides, right? If we close this container from both sides, it means that the piston of this container, if there is a piston, right, if this is the piston of this container, this piston should be immovable, right? This piston should be immovable. Then only the volume of this container will remain constant. Otherwise, if the piston is movable, then upon increasing the temperature, the piston may slide up, then the volume of the container will not remain constant. So piston should be fixed on both sides, right? So that the volume of the container remains constant. What we do is that if we increase the temperature, then the pressure of this gas is also going to increase, right? Or if we decrease the temperature, then the pressure of this gas is also going to decrease. So according to Gay-Lussac's law, the pressure is directly proportional to the temperature at constant volume, right? At constant volume. So if we keep the temperature of a volume of a container constant, right, then the pressure of the uh, gas, because of the gas in a container, will be proportional to the temperature. So upon increasing the temperature, the pressure will increase. Upon decreasing the temperature, pressure will decrease. So from here we can say that the ratio P upon T, that's pressure and temperature ratio, will always be a constant, right? So the ratio of temperature and the pressure will be always a constant, or we can say that P1 T1 will be always equal to P2 T2 at constant volume, right? At constant volume. At constant volume, P by T will be always a constant, right? So this is what we call as the Gay-Lussac's law, right? Now, if we plot a graph between pressure and the temperature, right? Pressure and the temperature, then it will be a straight line passing through the origin, right? So pressure versus temperature, where temperature is in Kelvin scale, right? Temperature is in Kelvin scale. Then the pressure versus temperature will be a straight line passing through the origin, right? This will be the graph between pressure and temperature, right? At constant volume, right? Volume is constant. Volume of this gas is constant. So at constant volume, the pressure will be directly proportional to temperature, or it will be a graph, a straight line passing through the origin. Similarly, if we plot a graph, that what we call as indicator diagram, right? So the indicator diagram for this condition will be P versus V, right? The volume here is a constant, and pressure has to volume here is a constant, right? So at this point, if volume is constant, right? Volume is fixed, then pressure can increase and decrease, or we can say it will be a straight line. It will be a line passing parallel to the pressure axis, right? Because volume here is a constant, right? So this will be the graph between pressure and volume, right? Volume is a constant here, right? So this will be the indicator diagram between pressure and volume, right? Now, if we plot the same graph, if we plot the same graph for pressure versus temperature, but in the units of degree centigrade, right? We know that in that case, it will be a straight line, but it will have some slope, right? It will have some slope. It will not pass through the origin. So this will be the graph between pressure and temperature. Pressure and temperature. It will be a straight line, but not passing through the origin. It will have some intercept. right? So it will be having some intercept. Now, similarly, if you plot a graph, pressure versus 1 upon temperature, right? Pressure versus 1 upon temperature, right? Pressure versus 1 upon temperature. Now we know that P by T is a constant, right? P by T is a constant. Then pressure versus 1 upon temperature, it will be a hyperbolic graph, right? The pressure versus 1 upon temperature will be hyperbola in nature. So this will be the nature of the graph between pressure versus reciprocal of the temperature. So these are the four graphs that we plot with respect to the Gay-Lussac's law. First is the pressure versus temperature graph, second is pressure versus volume, and then pressure versus temperature in centigrade, degree centigrade, and then pressure versus 1 upon temperature, right? So let's move on to the next law, that's the Avogadro's law, right? Avogadro's law states that at same temperature and same pressure, right? For a given, if we have two containers, let's suppose we have two containers here. If we have the two containers, this is the container one and this is the container two, right? And in this container, we have some gas one, right? And in this second container, we have the gas two, right? In the second container, we have the gas two, right? Now let's suppose we have the hydrogen gas here and we have the oxygen here in this container, right? Now the Avogadro's law states that if the temperature of the two containers is same, the temperature here is T, the temperature here is T, and the pressure is here P, and the pressure in this container is also P, right? And the volume of this container is, right? Let's suppose volume of this container is B and the volume of this container is also B, right? Then the Avogadro law says that then the number of molecules of hydrogen present in this container, in container first, will be equal to the number of molecules of oxygen present in the container second, right? Or we can say, let's suppose N1 molecules are present in a hydrogen, N1 molecules of hydrogen are present in first container and N2 molecules of oxygen are present in second container. So with these conditions that volume is same, temperature is same, pressure is same, then they must contain the same number of molecules, right? So N1 will be equal to N2. So this is what we call as Avogadro's law. Avogadro law states that at constant at same temperature, pressure, and volume, right? At same temperature and pressure, equal volumes of all gases contain equal number of molecules, right? Provided P, V, and T are same for all the gases, right? So they will contain equal number of volumes, equal number of molecules. That's the Avogadro law, right? That's the Avogadro law, right? Now, let's look at this question. The question is that we have been given two hyperbolic graphs or pressure versus 1 upon temperature curves, right? Pressure versus 1 upon temperature curves. Find relation between V1 and V2 for given graph, right? V1 and V2 for a given graph. Now you can see here, let's suppose it's a graph between pressure versus temperature, right? Pressure versus temperature, 1 upon temperature, right? And we know that according to Gay-Lussac's law, right? According to Gay-Lussac's law, pressure is directly proportional to the temperature, right? Pressure is directly proportional to the temperature. Now it means that where the temperature is more, the pressure will also be more at constant volume if V is constant, right? If V is constant. Now, if I choose 2 points, if I draw a straight line parallel to pressure axis, it will intersect the two graphs at two different points, right? At two different points, right? Now you can see here at this point, right? At this point, the pressure is more, right? Pressure is more. Then at this point, the temperature has to be greater. Let's suppose temperature at this point is T2 and the pressure is P2. Now at this point, temperature is T1 and pressure is P1, right? So definitely T2 is greater than T1 because P2 is greater than P1, right? P2 is greater than P1, right? P2 is greater than P1, right? Now, Now at this point, you can see here that the temperature is a constant, right? The temperature we have fixed the 2 points here. The 2 points here are fixed. So T1 has to be equal to T2 because it's a straight line parallel to the pressure axis. So it means that we have fixed the temperature, right? We have fixed the temperature. If the temperature has been fixed, right? The temperature has been fixed. If the temperature at this point has been fixed, at the 2 points, if the temperature has been fixed, then we know that pressure will be inversely proportional to the volume, right? So if we fix these 2 points here, right? If we fix these 2 points here, now at this point, the temperature will be same, right? Temperature will be same. That is T1 will be equal to T2, right? But here the pressure is P2 at this point and the pressure is P1 at this point, right? And if we fix the temperature, then pressure has to be inversely proportional to the volume, right? Volume. It means that P2 is greater than P1, right? P2 is greater than P1. It means that V1 has to be greater than V2, right? V1 has to be greater than V2. So this is the conclusion here, right? The volume in the first graph will be greater than the volume in the second graph, right? So V1 has to be greater than V2, right? Now let's move on to the next question. The next question says that at a particular temperature and pressure, 4 moles of N2 occupy a volume of 30 liters, right? Then find volume occupied by 16 moles of O2 at same temperature and pressure, right? So we can use ideal gas equation, right? Let's suppose if we use the ideal gas equation, PV is equal to nRT, right? PV is equal to nRT. Now the question is that at a particular temperature and pressure, 4 moles of N2 occupy a volume of 30 liters, right? They occupy the volume of 30 liters, right? So we can write here the equation V upon N, right? V upon N will be equal to RT upon P, right? Now the pressure and temperature here is a constant, right? Pressure and temperature here is constant or is also a constant. We can write V1 by N1 has to be equal to V2 by N2, right? It has to be equal to V2 by N2. Now 4 moles of N2 occupy a volume of 30 liters. Then find volume occupied by 16 moles of O2, right? So it occupies a 30 liters with a mole with number of moles equal to 4. Then we have to calculate the volume of 16 moles of O2, right? We'll just multiply here with 16, it will be 4, right? So V2 here will be equal to 4 multiplied with 30, that will be equal to 120 liters, right? So it means that the 16 moles of oxygen will occupy 120 liters here, right? So 120 liters of the volume will be occupied by the 16 moles of the oxygen, right? Now let's talk about the different types of speeds of gas, right? Different types of speeds of gas molecules, right? So first we will discuss about the average velocity, then average speed or mean speed, then most probable velocity, and the root mean square speed, right? Now average velocity, we know that it's for a single particle, we define average velocity as total displacement, right? It's defined as the total displacement upon the total time, right? Total displacement upon total time, right? Total time, right? Now we know that when we keep a gas molecules in a container, right? We keep a gas molecules in a container, right? Gas is placed in a container, and these gas molecules, according to the kinetic theory, they are in a random zigzag motion, right? They are continuously in a random zigzag motion. If they are continuously in a random zigzag motion, then it means that the particle will collide with each other and also at the walls of the container, right? Let's suppose this particle collides this particle, and here it goes to strikes to the wall of the container, it will come back, right? And after that it will again strike this particle and will again come back, right? Now let's suppose after some time t, this particle actually came back to its original position after some time t through different collisions, right? Through different collisions. So we can say here the displacement of this gas molecule now here is zero, right? Upon the time t, that will be zero, right? It means the average speed of each and every gas molecule here is zero, because after some time t, these gas molecules will come back to their original position, right? So this will happen to each and every gas molecule, right? That's why we say that the average velocity of gas molecules is equal to zero, because they are in a random motion in all possible direction with all possible velocities, right? Therefore, we say that the average velocity of the gas molecules in container is zero, right? The average velocity of the gas molecules in container is zero, right? Now, talking about the average speed, so average speed will not be zero. Average speed will be a non-zero quantity, right? It will be a non-zero quantity, right? So average speed of gas molecules will be a non-zero quantity. So average speed is nothing. Let's suppose we have gas molecules of different speeds. Let's suppose V1 and V2, right? V2, V3, and so on, right? Up to Vn. Then modulus of this velocity will give us the speed, right? Then the average of those speeds, what we call as average speed of the gas molecules, right? So it's nothing, or we can say that it's a total distance traveled by the total time, or we can say if we add the speeds of each and every particle, right, divided by the total number of particles, this will give us the average speed of the particle or gas molecules, right? Now talking about the most probable speed, right? Most probable speeds at a given temperature, the speed which is to which maximum number of molecules belongs, right, that's what we call as most probable speed, or we can say the speed possessed by maximum number of particles, maximum number of gas particles or gas molecules in a container, that's at a given temperature, that's what we call as most probable speed, right? That's what we call as the most probable speed. And rms speed is defined as root mean square speed. It is equal to the square root of the sum of squares of speed of each molecule of a given gas, right? We can define this RMS speed as we just RMS value. If we read it in a reverse direction, it means if we square the speeds, then take the mean of that speed and then take the root of that mean square, right? We take the root of that mean square speed, right? So that's what we call as the true RMS value, right? It means that let's suppose we have three gas particles. Let's suppose we have three gas particles with speeds V1, V2, and V3. We have to define their RMS. Then what we'll do is that we'll just first square their speeds. That's V1 square, V2 square, right? V3 square. Then take a mean of their speeds. That will be V1 square plus V2 square plus V3 square, right? Upon 3, right? This will be the mean. Then taking the root of these mean square speed, that will be V1 square plus V2 square plus V3 square upon 3. That's what we call as VRMS, right? This is VRMS. So this is how we define the VRMS of a gas, right? Root mean square speed of a gas, right? Now you can see here four gas molecules have speeds 3u, 5u, 2u, and 6u. Find their RMS speed, right? So their RMS speed will be nothing. What we'll do here is that we'll just first of all take the square of these speeds, right? We have to find VRMS. So first of all, what we'll do is we'll just square their speeds. That will be 3u square, right? Then 5u square, 2u square, and 6u square, right? Now we'll take the mean of these square of the speeds, right? So we call it as VMS. That's mean square speeds, right? That will be 3u whole square uh, plus 5u whole square plus 2u whole square, right? Plus 6u whole square, right? Divided by 4, right? That will be equal to 9u square, 25u square plus 4u square plus 36u square upon 4, right? So that will be equal to, so 36 plus 9 will be equal to 45. 45 plus 25 will be 70, and 70 plus 4 will be 74, right? It has to be 74. So we'll check it again. That's 9 plus 25 u square, right? Okay, that's 4 u square and 36 u square. So it will be 40, 65, 94 u square upon 4, right? Now what we have to do is that we'll take the root of this mean square. We will get the RMS value. That's VRMS, right? So VRMS will be under root of 74 u square upon 4, right? You can write it as u by 2 root 74. So this is the VRMS value, right? This is the VRMS value, right? Now for the above same question, if we have to calculate the average speed, right? Average speed. So average speed will be nothing. It will be 3u plus 5u plus 2u plus 6u, right? Upon 4, right? That will be equal to 8, 8, 11, 11 and 5 is 16. That's 16u upon 4. That will be equal to 4u, right? 4u. So this will be the average speed, right? You can see here the average speed is different that of root mean square speed, right? It's different from that of root mean square speed, right? Now let's talk about the distribution of the velocities of or speeds of gas molecules, right? So this distribution was studied by Max and Boltzmann, right? So Maxwell and Boltzmann actually plotted a graph, and they put forward a distribution of the gas molecule theory for the distribution of the speeds of gas molecules, right? So they plotted a graph between number of molecules and velocity of molecules, right? So number of molecules, right, with the velocity as a function of temperature, right, as a function of temperature at different temperature, right, with the velocity of molecules, right, or speed of molecule, we can say that. You can see here that this was the curve obtained, right? This was the curve obtained at different temperatures, right? So for the first, for T1 500 Kelvin, right? 500 Kelvin is for at a temperature of 500 Kelvin. This is the peak observed, and then if we increase the temperature, the peak shifts. Peak shifts in the downward direction and graph moves in the rightward direction, right? And similarly, if we further increase the temperature from 1000 Kelvin to 2000 Kelvin, the peak once again shifts in the downward direction and the graph shifts towards the right, right. So it means that it actually tells us that if at any particular point it will give us the number of molecules possessing a particular speed, right. Let's suppose this is the point, and if this point intersects the x-axis, right, at this point, right? Then at this point, it will tell us the number of gas molecules, right? That is possessing this V1 speed, and similarly, it will tell us the number of molecules that's actually possessing V2 speed, and the number of molecules that actually possess V3 speed, right? So actually, this distribution tells us about the different speeds possessed by different number of particles, right? So the you can see here there is a speed, there is a maximum here, peak here, which is actually which belongs to the maximum number of particles, right? And this speed which is possessed by the maximum number of the particles, this speed we call as most probable speed, right? It's the most probable speed. This is what we call as most probable speed. So this is what we call as most probable speed, right? So this speed is actually possessed by the maximum number of particles. Now, what happens is that if we further increase the temperature from 500 Kelvin, from 500 Kelvin to 1000 Kelvin in the downward direction, and the graph shifts towards the right, it means that you can see here it actually means that the most probable speed has actually decreased, or we can say the number of particles possessing the most probable speed actually at a given temperature has decreased, right? It has actually decreased, and the curve has shifted towards the right. The curve has shifted towards the right. The important conclusion for this area under this curve is that this area number of particles present in a gas, right? Number of particles present in a gas. So it actually gives us the number of particles present in a gas, right? Okay. So we know that the total number of particles present in a gas container is actually a constant, right? If we further increase the temperature, right? If we further increase the temperature, it means that upon increasing the temperature, the speeds of the particles will actually increase, right? Be it most probable speed, be it RMS speed, right? But the number of particles possessing that most probable speed will actually decrease upon increasing the temperature, right? It will actually decrease upon increasing the temperature. And upon further increasing the temperature, the graph will still shift towards the right, right? So if the graph shifts towards the right, it means the peak has to come downwards, right? Peak has to come downwards. It means the total area has to remain constant for this graph, because the number of particles present in a container is always a constant, right? That's the reason we say that the graph will shift towards the right upon increasing the temperature, and the peak will shift in the downward direction, right? For the condition T3 greater than T2 greater than T1, right? Now, there are certain conclusions that the velocities of molecules of a gas are in between 0 and infinity, right? You can see here it's between 0 and infinity. The velocities of the gas molecules are between 0 and infinity. The area of the graph with velocity axis gives us actually the total number of molecules available in the container, which remains constant always, right? And upon increase in the temperature, with the increase in the temperature, the most probable velocity increases, but corresponding number of molecules, it means the number of molecules which actually possess the most probable speed before actually decreases upon increasing the temperature, right? The number of molecules within a certain range, within a certain velocity range is constant, although the velocity of a molecule changes continuously at particular temperature. It's a very important conclusion that the number of particles in a certain range of velocity, right? The number of particles in a given range of velocity is always a constant, right? So there will always be the same number of particles with a certain range of the velocity, right? Now let's discuss this question. If for a gas, their most probable speed at temperature T1 is V, and at temperature T2 is 3V by 2, and at a temperature T3 is 2V by 3, we have to find the order of temperature, right? So we know that upon increasing the temperature, the most probable speed, upon increasing the most probable speed will actually increase, right? Upon increasing the temperature, the most probable speed will increase because you know that upon increasing the temperature, the graph shifts towards the right, right? The graph shifts towards the right. The number of molecule possessing the most probable speed actually decreases, but the most probable speed increases, right? So increasing the temperature, the most probable speed will increase. We can say that uh, most probable speed is actually proportional to the root of temperature, right? It's actually proportional to the root of temperature, right? So upon increasing the temperature, the most probable speed will increase, right? So you can see here the maximum is 3v by 2, and then we have at T3 we have 2v by 3, and T1 we have v, right? It means that the at temperature T2, the T2 will be the greatest of all temperatures, right? Then we will have T1, and then we will have T3, right? So it means that the T2 should be greater than T1, and T1 should be greater than T3, right? So upon increasing the temperature, the most probable speed increases, the RMS value of the speed increases, the average speed also increases, right? So upon increasing the temperature, the most probable speed increases, right? And the graph shifts towards the right, but the number of molecules possessing the most probable speed actually decreases upon increasing the temperature, right? So we can say that VRMS is always greater than V average, right? And it's always greater than V most probable, right? Among all these speeds, the RMS speed has always the greater value than the average speed and the most probable speed, right? So this is the conclusion. These are few conclusions from the Max Boltzman distribution, right? Max Boltzman distribution. The first conclusion was that the velocities of molecules of a gas are in between 0 and infinity, right? They are in between 0 and infinity. The area of the graph with velocity axis gives us total number of molecules available in the container, which remains constant always, right? Upon increase in the temperature, the most probable velocity increases, but corresponding number of molecules decrease, right? Because upon increasing the temperature, the number of molecules possessing the most probable speed actually decrease, right? And there is always a fixed number of molecules which are having the speed in a given or in a certain range of velocity, right? So this was about the Max Boltzmann distribution, right? In the next lecture, we'll be starting with the thermodynamics, right? We'll be starting with the thermodynamics, and we'll be discussing some of the uh, uh, questions with respect to the kinetic theory, right? And some of the more conclusion with respect to Max Boltzmann distribution, and then we'll be starting with the thermodynamics, laws of thermodynamics, right? And different thermodynamic processes as well, right? So that will be studied in the next lecture. Till then, take care and goodbye.